welcome to this video on the road to quantum reality. If, like me, you are curious about the way the natural world works, then you have probably discovered that quantum mechanics is as frustrating a subject as it is fascinating. If you've clicked on this video in the hope that you can relieve some of this frustration, then I hope we can help each other. In my own study of the subject, I quite soon came to the realization that trying to interpret it as it is not a fruitful approach. I think it has been a victim of its own success because it makes such accurate predictions about how the quantum world behaves that it becomes difficult to challenge its inherent assumptions and the weird and counterintuitive interpretations to which they lead. I decided that if you want to understand quantum mechanics, then quantum mechanics is not the right place to start. A bit like the stranger asking for directions from a local, only to be told I wouldn't start from here. Instead, I have tried to develop a theory from the ground up, so to speak, in such a manner that it had some chances of replicating quantum-like features. That way, if and when such features emerged, I would know how to interpret them, and so perhaps get some insight into quantum mechanics. You are probably thinking that this approach is very unlikely to succeed. After 100 years, any such theory would already have emerged. But I think it is a case of seek and you will find. The absolutist approach of some of the founding fathers of quantum mechanics, with the honourable exception of Einstein, Schrodinger, de Broglie and later Bohm, almost prohibited generations of physicists from looking. To my amazement, the approach has been successful beyond my wildest dreams. I would love for you to share the excitement of the journey with me in this series of videos. Okay, let's get started. First, look at these images. Perhaps you recognise them. But if not, let's ask an imaginary friendly physicist what they represent. In all likelihood, they will recognise that these are solutions to Schrodinger's equation in 2 dimensions. Because of the triangular form with 1 in the first row, 2 in the second, and so on, our friend may also be able to identify that these patterns relate to the simple harmonic oscillator potential. That's a potential which is shaped like this parabola. Our friendly physicist might clarify the meaning of the potential by telling us that if the electron were a charged point particle and there was a positive charge at the centre of the diagrams, this parabolic shape would describe the potential energy of the electron particle at each point. So near the centre, the electron would have the lowest potential energy. Continuing the explanation, we might be told that the triangular pattern is typical of simple harmonic oscillator potential in 2 dimensions, and each row contains forms having the same distinct energy. The rows are called degeneracy groups. The single shape at the top is the lowest energy. The shape is smaller, so the potential energy is lower. At the risk of straining our relationship a little, we might ask our friend the naive question, what is psi? And be told, well, it's a field of complex numbers. Each point in space has a complex number associated with it. The actual pictures are of psi multiplied by its complex conjugate, which is just a mathematical procedure to give us a real number which can be plotted on the diagrams. So the psi we are looking at is a mathematical function which is the solution of Schrodinger's equation for this potential. Undaunted, we press on with childlike questions. Does psi describe something real, like a pressure or a density? And we might see the sadness in our mentor's eyes as he tells us, no, it's a probability density. It has no immediate physical reality. Finally, we reveal our duplicity to our poor, probably now ex-friend. They have been deceived. There is something we didn't tell them. These graphs were not obtained by solving Schrodinger's equation. They were calculated using a completely different approach, which I have called, for want of a better name, real-wave quantum mechanics. But we can give some consolation. They are for a 2D state, and they are the results for a simple harmonic oscillator potential. We now need to explain how our friend has been tricked. As a taster, real-wave quantum mechanics is based on acoustic waves in a physical medium, so think perhaps of a perfect gas. The medium must possess mass so that it is capable of having internal momentum where it ebbs and flows. Although you can't see it in the diagrams because they are far too small, the fields are not continuous. They actually contain a very large number of interacting vortices. The link to the equivalent Schrodinger complex field is that the phase and magnitude of each vortex, which can be associated with its angular momentum, is the same as the continuous field at the vortex location. I haven't shown how the figures were obtained yet, so you will have to take my word for it for now. But an obvious question that our friendly physicist, and indeed any scientifically minded observer, might ask is, have you just lucked onto a peculiar system that just happens to obey Schrodinger's equation in this one respect? And of course, it's a very fair question. But let's go just a bit further. Keeping in mind that the interpretation of quantum mechanics is a nightmare, let's take one specific aspect. The perennial interpretation problem, what is spin? It is indisputably experimentally established that electrons have an angular momentum which we call spin, and that it has a value of h bar over 2. Within quantum mechanics, while it is conceivable that we could model orbital angular momentum in terms of a changing probability, there is no way for it to model electron spin. But if we revert to a picture of an electron as essentially point-like, it also becomes impossible for that to model angular momentum, for the simple reason that angular momentum is given by the product of the momentum and the radius has to be 0 for a point particle. We have another Bohr-like moment, as when he declared that electrons moving in an orbit do not radiate energy. In this case, we just say that spin is intrinsic, meaning we haven't a clue why, but there it is. But the real-wave quantum mechanics model contains a myriad of rotating vortices, and each one contains a small amount of angular momentum. And if you add them all up, you get h bar over 2. Wow. Spin in real-wave quantum mechanics is not intrinsic. It has a completely realistic interpretation. Now, of course, we can still stick to the "that's lucky" view, but this is only the start. If you follow these videos, you will see that these parallel insights keep cropping up. For example, we can establish exactly why it is that Schrodinger's equation results can be found by the alternate calculations of real-wave quantum mechanics. We get considerable insight into what causes electrons to be fermions and the reason why they obey the Pauli Exclusion principle. The reason why structures have different energies is revealed. It is much more beautiful than saying that it is because electrons are closer to the positive proton. In fact, it brings the meaning of what a charge is into question. And if we are not modelling particles whizzing around in some sort of orbits, we have to explain how it is that some structures can have orbital angular momentum. We will do this, and how it occurs is very revealing. It will not have escaped your notice that I have described real-wave quantum mechanics in terms of real waves in some medium. You could say it is based on an ether. Surely that is going to be a problem for special relativity. In fact, once the dust had settled on special relativity, Einstein was at some pains to point out that it did not preclude an ether, but it did preclude asking questions about its state of motion. In fact, real-wave quantum mechanics leads to special relativity as its asymptotic behaviour at low speeds. Low relative to the speed of light, that is. Such low speeds include all of the things that concern us normally, such as knowing how clocks will slow down in GPS satellites. What happens at higher speeds is an open question for the moment. Richard Feynman wrote that every self-respecting physicist should write alpha on their blackboard and worry about where it came from. Real-wave quantum mechanics requires the use of a dimensionless factor, in fact the ratio of how much energy vortices re-radiate as a fraction of what they receive. The value chosen impacts the size of the structures, so it is reasonable to assume that there is a particular value which would match real-wave quantum mechanics to quantum mechanics. Could that be what the alpha of quantum mechanics is? It could be just lucky to come up with something that matches quantum mechanics regarding structure and spin, but as these things begin to pile up, the big question becomes, are we now able to give quantum mechanics a realistic interpretation? In fact, is quantum mechanics actually real-wave quantum mechanics? I'm hoping you will be able to join me on this journey. It's not going to require a huge amount of maths, and you're not going to be drowned in equations and lost on page 2, so to speak. A lot of the findings come from computer calculations. The principles are so simple, you might even like to try writing your own code. Please like and subscribe and tell all your friends and colleagues. My goal is to reach a situation where no physicist can claim not to have heard of the possibility of a realistic interpretation of quantum mechanics. Meanwhile, I will leave you with a three-dimensional structure calculated using real-wave quantum